Okay, so in this section, as I said, we're going to do word problems, and all of our word problems are based on a logarithmic scale. So the common log has a base of 10, and each one of these, pH, earthquakes, and sound intensity, are also based on a logarithmic scale. So it makes it a perfect fit for log word problems. Okay, so let's talk about pH first. So pH is the potential for hydrogen, and it is based on numbers from 0 to 14. So 7 right in the middle is neutral, and anything from 0 to 7 is considered acidic. Anything from above 7 up to 14 is considered basic. Now, I'm not a chemistry person, so what helps me memorize this is it's in alphabetical order. A, acidic first, B, basic second, in alphabetical order. So the reason that I write my scale like this is to show you that as I increase by a factor of 1, I'm going to have really a tenfold difference in intensity. So right here, a difference of 1 unit in pH corresponds to a factor of 10 difference in intensity. So let's look at this as an example. Now pH is a little bit different than all the other ones because it's split into two parts, acidity and basic. So in the top part of my number line, going from 7 down to 0, the smaller the number, the more acidic. In the second part of the number line, anything above 7 as I go up to 14 becomes more basic. So it's kind of going from opposite directions from 7. So if I have, for example, a pH level of 3 and a pH level of 5, so these are 2 units away on the pH scale. But each time I go up a unit, it's a factor of 10. So it's like saying the difference is 2, but the intensity is 2 factors of 10. Well, 2 factors of 10, 10 squared, is just 10 times 10 or 100. So what that would tell me is that a pH of 3, and see it's more acidic because it's a smaller number, is 100 times more acidic than a pH of 5. Now, if I look on the other side of the scale, let's say I had a pH of 12 and 9. So you can see that those are 3 units apart, which means they are 3 factors of 10 apart in intensity. So 3 factors of 10 would be 10 cubed, or 10 times 10 times 10, which is 1,000. So 12 is the bigger number, and that means it's more basic. How much more basic? It's 1,000 times more basic than a pH of 9. So we're going to use this scale to help us for all 3 types of word problems, and that helps us with the intensity factors. In terms of figuring out pH and hydrogen, we can use this formula, which will be given to us on all of the questions. So pH is equal to negative log of hydrogen. Notice there isn't a base for that log. I could really write it like this, base 10 of hydrogen. Okay, so it has that invisible base of 10. Now, pH again is a number between 0 and 14. Hydrogen, however, is the hydrogen ion concentration. It will always be written in scientific notation. So let's try some examples. Before I begin that, a little note. The higher the pH is not more acidic. That's so basic. Little chemistry joke for you. Again, remember my little trick of acidity and basic, and from the neutral they go in opposite directions. More acidic here, more basic here. Okay, so looking at the first question, suppose you test some ammonia and decide or determine that the hydrogen ion concentration is 1.3 times 10 to the negative 9, and that would be moles per liter, I believe, is the units for hydrogen. Find the pH value. So I'm going to take my hydrogen concentration and just plug it in there. So I'm going to have that my pH level is negative the log of hydrogen, 1.3 times 10 to the negative 1. And then all I really have to do is plug this into my calculator, and I would get, pH is usually to the nearest tenth, I would get a pH value of about 8.9. Okay, that's the first type of questions. Let's look at going backwards where we want to find the hydrogen. So suppose you test apple juice and find that the pH level is 3.5. Find the hydrogen ion concentration. So this time I have pH of 3.5, which I'll substitute in there. So I've got 3.5 equals negative log of hydrogen. Now remember there's that invisible base of 10. So I can rewrite this as log base 10 of hydrogen. So it looks like I'm going to have to use circle of logs to go into exponential form. But before I can do that, I need to isolate my log. So I'm going to divide both sides by -1. So then I'll have -3.5 equals log base 10 of hydrogen. And now I can do my circle of logs. So using my circle of logs, I get that hydrogen is 10 to the -3.5. Now, for all of you that have taken chemistry before, you probably already know that hydrogen is 10 to the negative pH. And I get asked all the time, Ms. Gatos, can I just use 10 to the negative pH? Because I already know from chemistry that that works. And my answer to that is absolutely. So if you're not a chem person like me, you probably want to do all the steps. But if you already know that that's the shortcut, you can just go to that and you'll still get the same answer. You don't have to show all that work. So here it is, 10 to the negative pH, or 10 to the -3.5. Here's my answer. But remember I said hydrogen is written in scientific notation. So I usually write, I don't worry about significant digits. I usually do it to the nearest hundredth. So 3.16 times 10 to the E stands for exponent. So it's to the exponent of -4. So you just need to recognize the way that the calculator puts this in scientific notation. And that's what this is. I know it's in scientific notation because of that E standing for exponent. Okay, so let's look at some intensity questions. So a common ingredient in cola drinks is phosphoric acid. Oh, that sounds delicious. It's the same ingredient found in many rust removers, which is probably why you've seen those experiments where they have a glass of Coca-Cola and they put a nail in there and it actually disintegrates it. Okay, so a cola drink has a pH of 2.5. So right about here, 2.5 is my cola drink. Milk has a pH of 6.6. So looking at this scale, I know, oh, I slipped that up a little bit. Let's move that down. Okay, so looking at my pH scale, I know since cola has the smaller number, it is more acidic. And we're trying to find out how much more acidic it is. Okay, so just like we started before, we look at the difference on the pH scale. So the difference between these, 6.6 take away 2.5, is 4.1. So they are 4.1 units apart. But remember, for the intensity, every unit of 1 is a factor of 10. So this is like saying I have 4.1 factors of 10, or I have 10 to the exponent of 4.1 factors. So 10 to the exponent of 4.1 will give us the intensity difference. So since cola is the smaller number, it will be the more intense or the more acidic answer. So 10 to the exponent of 4, I can just plug that into my calculator and I get that number, so I'll round it to the nearest whole number. So now I can know that cola is 12,589 times more acidic than milk. So again, pH is the one that's a little trickier because it's not just a standard 0 to 14. You have to know the direction that you're going. So just remember 7 is neutral in the middle. Acidic comes before basic, alphabetical order, and then just compare the two to find the intensity factor. Okay, let's try another one where we're going to solve for the pH. So we have an apple that is 5 times more acidic than a pear. If a pear measures 3.8 pH, so this is my pear, what is the pH of the apple? So this time I'm given my intensity factor, which is 5 times. So I know every change in the pH scale is a factor of 10. So since it's only 5 times as acidic, I know that those numbers are going to be pretty close together, less than 1 unit apart. So somewhere in between 3 and 4, because they're not, or sorry, actually in between 2.8 and 3.8, because they're less than a unit apart, is going to be the apple pH. So I know it's a smaller number because remember, the smaller the number, the more acidic it is. So I need to look at the difference between these. So 3.8 take away the pH of an apple is how far apart they are. And how far apart they are is going to tell me how many factors of 10. So it's going to be 10 to the 3.8 take away apple pH. That will give me my intensity of 5. So what I need to do for this question is change it to log form using Bay. So I'll use Bay, so that is log of base answer equals the exponent. And then I just need to solve for the pH of apple. So I'm going to subtract 3.8 from both sides. Now, log base 10 is really just log of 5, common log, equals negative apple. And then I just need to divide both sides by -1 to get the pH for apple by itself. So log base 5 of 3.8, all divided by -1, will give me my apple pH. Okay, so I'm going to put that into my calculator. And you can see here, I do get a smaller number, which I was hoping, and they're pretty close together, pH of 3.1. So apple has a pH of 3.1. Okay, so we're going to take this idea of log scales and we're going to move it to Richter scale. Okay, so Richter scale is also based on the log scale. So Richter measures the size of earthquakes. So the same idea. Each level that you go up, each change in the Richter scale of 1 unit represents a factor of 10 times the intensity. So for example, if we have an earthquake measuring 4 and 1 on the Richter scale, 4 and 1. Okay, now this is nice because we're just increasing. Okay, so 4 is 3 units bigger than 1, which means the intensity is 3 factors of 10, or 10 cubed, which is 10 times 10 times 10, or 1,000. So a Richter scale of 4 is 1,000 times more intense than a Richter scale of 1. Similarly, if I had 6 and 8. So 8 is more intense, and since they are 2 times apart, they are 2 factors of 10 times more intense. So 2 factors of 10, 10 squared, or 10 times 10 is 100. So Richter scale of 8 is 100 times more intense than a Richter scale of 6. Or conversely, you can say that a Richter scale of 6 is 100 times less intense than a Richter scale of 8. So more intense, moving bigger, less intense would be the smaller. So either way is fine. So let's just look at Richter scale and kind of see what that actually means. I'm always interested to see like the real life application. So Richter scale measures from 0 to 10. So it takes about a Richter scale of 4 or bigger for you to feel it. So if you look at right here, you're not going to really feel vibrations of a passing truck too much. Okay, so anything bigger than 4, you're going to start to feel. So between 4 and 4.9, we might break some windows, small objects might fall, and you can see as I increase in the Richter scale, the more the damage increases. So the most powerful earthquake to date ever recorded was a 9.5 on the Richter scale in Chile in 1960. So 9.5, that would be 9 and over. That's near total destruction. So that is a very intense earthquake. We don't really experience too many of those in Calgary, so it's good to see some of the references there. Okay, so let's try an example. So here's a diploma example. So because I'm using a 10-point scale, or factors of 10, a log scale, I don't even need my formulas. So this whole question here, I can just zone in on this part right here and the question. So I don't even pay attention to the equation because I don't even use one. I just kind of use what I know about logs and log scales to do it. So in 1906, the San Francisco Bay Area had an earthquake that measured a magnitude of 7.8 on the Richter scale. So 7.8, and this is the San Francisco earthquake. What is the magnitude of an earthquake that is 158 times less intense? So less intense means it's below. So we're looking for the earthquake. I'm going to call it the other earthquake that was less intense. So since it's less intense, the intensity factor is not 158. It's less intense, so it's 1 over 158. So as I go up on the scale, I'm increasing by factors of 10. As I go down on the scale, I'm decreasing by factors of 10. So I'm going to set up my equation like this. So I'm looking at less intense. So I'm going to focus on the less intense. So I'm going to have 10 to the other earthquake, I'll call it x, minus 7.8. That will equal to the intensity factor of 1 over 158. So since I'm looking at less intense, it's a fraction. And since I'm looking at less intense, I'm starting with the less intense one. Okay, so looking at this, I now have my equation. I'm going to use Bay to switch it into log form. So Bay to switch it into log form. So I'm going to have log of base, A stands for answer, E stands for equals exponent. And then to solve for x, I'm going to add 7.8 to both sides. Add 7.8 to both sides, so that's gone. So log base 10 is just a log. So log of 1 over 158 plus 7.8 will give me my magnitude of my other earthquake, the less intense earthquake. So I know I've done this correctly if I have a number that's smaller than 7.8. So I just plug it into my calculator like that, and I get that it measures 5.6 on the Richter scale. So whenever you guys are doing the adding, subtracting for the exponent, just add or subtract in the direction of the increase or the decrease, whichever is given to you. Okay, let's try another one. So again, we have an earthquake intensity. I don't need the formula. I just zone in on the important information. So an earthquake measuring 5.3 on the Richter scale is 125 times more intense than a second earthquake. So now, since I'm more intense, I have a whole number intensity factor. So here's my 5.3 right about there. And this is the more intense one. So we're trying to solve for the less intense one. We're trying to figure out what the other one is. So I don't know what it is, but it's less than the 5.3. The other earthquake is right down here somewhere. Less than 5.3. So since I'm given something that is more intense, I'm going to have a whole number intensity, and I do the subtraction in the more intense. So I subtract in the direction of the increase. So this time I'm going to do 5.3 take away my other one. So I'm going to have 10 to the 5.3 take away my other earthquake. Richter scale is going to be 125. So I just want to make sure you guys know the difference of these ones. So this one here, again, we were focusing on the less intense. So we're subtracting in the direction of the decrease. So the decrease minus the 7.8 equals the less intense, so it's 1 over 158. This time we're given that it's 125 times more intense. So we're subtracting in the direction of the increase, which is why I do 5.3 take away the other equals to this whole number. Okay, so to solve for this, I'm going to use Bay. So to switch to log form, because we love logs. So it's going to be base answer equals exponent. Oops, minus. Okay, so to solve for x, I'm going to subtract 5.3 from both sides. So log base 10 is just a common log. And then I'll divide both sides by -1. So x is going to be log of 125 minus 5.3, all divided by -1. So I can put that into my calculator, and I should expect to see a number less than 5.3. And you can see I get a number of 3.2. So that means that the other earthquake had 3.2 on the Richter scale. Okay, let's move on to our last unit, part of word problems, which is decibels. So decibels are also based on the logarithmic scale. Now these ones are a little bit different. So pH and decibels are the ones that are a little bit different. So pH is different because we had kind of two different parts of the number line, above 7 and below 7. Decibels are a little bit different because we're going up by units of 10. So decibels measure the level of sound. And they were really created by or named after the inventor of sound, or the discovery of sound, Graham Alexander Bell. So we used to use a Bell scale, which is a change of 1. So 1 unit increase on the Bell scale would be a 10, because it's a log scale, a 10-fold increase in intensity. But we now use decibels. And what you need to know about decibels is that we're going up by units of 10. So every increase of 10 on the decibel scale, so if I go up by 1 unit of 10, 2 units of 10, it's going to be a 10 increase in intensity. The reason that is because 10 decibels are equal to 1 bell. So we primarily work in decibels, moving or measuring sound, but I want you to know that 10 decibels is equal to a bell, and you'll see where that's going to come into play. So what this means is that every time we increase in 10 decibels going up the scale, it represents 10 times more power or intensity in the sound wave. So let's look at an example. If we have the sound of a car engine at 70 decibels, versus a whisper at 20 decibels, those are a difference of 5 units. Units going up by 10 decibels. So since it's a difference of 5 units, that means the intensity is 5 factors of 10, or 10 exponent 5. So 10 times 10 times 10 times 10 times 10 is 100,000 times more intense. So the car engine at 70 decibels is 100,000 times more intense than the sound at 20 decibels. So just to kind of put this into perspective so you kind of see what decibels are, here's some examples of some common objects that you can see for decibels. Okay, now interesting to note, extended exposure to about an 85 decibel sound. So if you are exposed for an extended period of time to any sounds over 85 decibels, it can actually cause hearing loss over time. So look at all of these things here. We have hair dryers, helicopters, trombones, police sirens, jet engines, fireworks. All of those things, if I'm exposed to those over an extended period of time, it's going to start to cause hearing loss. So definitely important to protect your ears. Okay, so that's just how decibels work and some of the common ones that are there. Let's try some questions. I have 2 questions that we can try. So first question, how many more times intense is a referee's whistle of 125 decibels? So the whistle is right about there, compared to a whisper of 22 decibels. That's quite a distance. Okay, so if I look at how far apart those are, okay, those are 103 decibels apart. If I just did 125, take away the 22, they're 103 decibels apart. But remember, our scale is in factors of 10, so they are actually 10.3 units apart. So the intensity difference between those will be 10.3 factors of 10, or 10 to the 10.3 times difference of intensity. So that means that the whistle is 10 to the exponent of 10.3 times more intense than the whisper. That's going to be a really big number. So when I put it into my calculator, it's actually so big that the calculator puts it into scientific notation. So this means 1.995262315 times 10 to the exponent of 10. So let's just move our decimal place over 10 units. So I'm going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, and I just need another 0 in there to finish it off. Okay, so this is going to be 19952623150 times more intense. So the whistle is this many times intense than a whisper. Okay, let's look at what this number actually is. We're going to go in groups of 3 here. Okay, so that's going to be 19,952,623,150 times more intense than a whisper. That's a big difference. Okay, let's try another one. This one's a diploma example. So again, the nice thing about using this log scale and what we know about logs is that we just have to focus in on these parts here. We don't need the formula. So it's really good. We don't have to memorize a formula. We're using intuition and understanding of log scales to solve these questions. So during an international soccer tournament in 2010, a noisemaker called the Vuvuzela, maybe, had a measured loudness of 127 decibels at full volume. That's pretty loud. 127 decibels. If the intensity of this noisemaker is 5,000 times greater than the intensity of a sound of a lawnmower, then the measured loudness of a lawnmower to the nearest decibel is what? Okay, so the lawnmower is down here somewhere. Lawnmower. Okay, that looks like lawn mover. Let's try that again. Lawnmower. So it's somewhere down here because this one here is more intense. Okay, so I don't know what the lawnmower is, okay, but the difference between them is going to be 127 decibels. Take away whatever the intensity, or sorry, whatever the decibel sound level of a lawnmower is. But again, remember that we work in bells, not in decibels, because this is a factor of 10. So every increase is a factor of 10. So the difference in the scale is 12.7 take away x, because we're going up by tens, not by ones. So subtract in the direction of the increase. So since this guy here is more intense, we're going to go 10 to the 12.7 take away x equals to the intensity factor. So since it's more intense, it is a whole number. Okay, so let me just move down. I need more room here. And we're going to solve this. Okay, so to solve this, I'm going to use switching to log form using Bay. So log base answer equals the exponent. And then I'm just going to solve for x. So I'm going to subtract 12.7 from both sides. So log base 10 is just a common log equals negative x. And then I'll just divide both sides by negative 1. So log of 5,000 take away 12.7 divided by negative 1 equals 2x. And then I can just put that into my calculator to figure out what my x value is. Okay, so that would be 9.0. So the lawnmower would be 9 units below the noisemaker. So if this here has a measure of 9 units and every unit goes up by 10, that means that the lawnmower would be 90 decibels because each unit of change is 10 decibels. So since this is saying it's 9 units on that scale, each unit measuring 10, the sound would be 20 decibels. So going back up here, yes, you can see that it is 90 decibels. Okay, so again, the only trick there with sound levels is that I'm going up by scale of 10, not a scale of 1. Okay, so let's summarize this. pH, Richter scale, decibel, all based on the log scale. So 1 unit in change in that scale represents an intensity change of 10-fold. So these are all multiples of 10. So as I go up in intensity, I'm increasing by multiples of 10. As I decrease down that scale, I'm going down by multiples of 10. Remember that pH is a number between 0 and 14, where the top half is acidic, the bottom half is basic, alphabetical order, A before B. Richter scale, number between 0 and 10. And remember that decibels are numbers between 0 and 140, increasing by units of 10 each time because we're dealing with decibels. So you guys do know that I love a good math joke, but I thought today, since we were doing word problems, I would switch it up, because really, how often do I tell chemistry jokes? Well, the answer to that is periodically, kind of like the periodic table. Okay, so you guys have questions 4 to 10 to do in my lesson notes here, and all the detailed solutions to those are on D2L. And then after you're done that, you can move on to the textbook questions, and this will conclude our lessons for Chapter 8. So I hope those helped, and we'll see you for our next unit.